holy crap, it was a monumental task to design these things. And yeah, what all things do we need to take into consideration, and how much time do we have, and what kind of problems do we run into? Stay tuned. So we're back in January-ish 2017. In last episode, yeah, we were over at World Time Attack 2016, met Rod, met Richard from PR Tech, looked at some the challenges they were facing and what they wanted to achieve with the engine, and we sat down and thought a little bit about how this would suit the development process for Elmer Racing and what we want to achieve. And so we have about 9 months now till World Time Attack 2017, which is the debut target for the engine, and we have absolutely nothing. We have no drawings, no start dimensions, or I mean some like bore spacing, for instance, from the factory Porsche engine. We want to retain that, for instance. But otherwise we're starting from a clean sheet. Will we make it or not? And what kind of design philosophy and stuff like that goes into this? Okay, so we start with the most important aspects, and that is, as it should come to no surprise for you guys following our channel, it's weight, or in the case of engine, of course, power to mass ratio, and of course some other aspects also, like how compact the engine is and stuff like that. So we went through some different options, rechecking everything, and inline 4 about this displacement is absolutely perfect for this sort of power goals. So we're looking at being able to produce about 1,500 horsepower, so that's more than what they wanted on the RP968. But yeah, we want to leave some margin there, and also we thought that for future sort of circuit racing use, this would probably be a good power level. So that is basically what the cooling system and the power output of this with low boost settings, basically. So I mean, the lower boost setting is you need the less work there is into mapping the ECU and doing the boost response and stuff like this. So definitely want to keep the boost levels low, so you can at the track concentrate on actually setting up the car and making it go fast instead of trying to get the throttle response nice or something like that. I mean, you can make 1,500 horsepower on a 2-liter or 2.5-liter engine, but yeah, with this 4-liter engine, so we're running, ended up with a 116 millimeter bore and 94 millimeter stroke on this. So the bore is, for instance, larger than a big block Chevy V8 bore. So we're also, of course, at the same time constraint, heavily time constraint. So trying to get everything done in 9 months is incredibly difficult. So we needed to develop this as efficiently as possible, and of course, like, offload some of the components that other companies or people could do, so that we save on the design and manufacturing time on the components that we have to do ourselves. And so we, for instance, one clear time saving measure was to get the pistons and connecting rods manufactured by another aftermarket company. They specialize in drag components, because at this power level there's really no sort of circuit racing applications or anything like that. I mean, we're at 1,500 horsepower for 4 cylinders, so that's 750 for 2 cylinders, or what is that, 375 horsepower, I believe, per cylinder. And those power levels are so high that you're not really going to find anything suitable in anything other than drag racing stuff. So yeah, we looked around, had a supplier that actually Rod suggested. I mean, that was one of those that we looked at, and spoke with them, and yeah, they were happy to do the connecting rod and the piston, because we also wanted to push the pin location on the piston up as high as possible to be able to run as long a rod as possible. I mean, the rod length isn't that important from an overall engine design perspective. You always want to make the engine more compact, even if that costs rod length. But we also wanted to keep some of the dimensions overall from the Porsche 968 engine, which was a very suitable size dimension. So keeping that deck height, so the crankshaft center line to the cylinder head flange surface, Keeping that, we could run a relatively sort of long connecting rod, but we still wanted to stretch that out as far as possible. But we also needed to have a inverse dome, I believe it's called, in the piston to get a larger combustion chamber volume. So there was a very limited amount of space for the small end on the connecting rod. So that's why we wanted to have one single company do the rod and the piston, so that we'll ensure that those actually fit together, and we don't end up in a situation where we have to redo the rod or redo the piston to be able to make those fit, or that the rod length needs to be adjusted because the piston pin height couldn't be done or something like that. And yeah, that proved out to be a really good solution. And yeah, we got that done very efficiently, and yeah, BME did that for us, so very happy with them so far. Let me show you guys some close-up details on this. Let me just fire up my close-up camera here. Yeah, so as you can see here, I mean, we have strengthening ribs here. Of course, ribs look really sexy, so it's important to have them just because of that. But also these do provide strengthening parts. So these bolt holes here are for the mounting to the chassis. These are in the factory Porsche 968 location, so that it again maintains some regulation compliance, so that you can motivate that it is based on a factory engine. And yeah, this rib here, so this is actually the main oil ducting underneath here. And yeah, we have a thin wall surface around here, and yeah, designed to be manufactured from 5-axis stuff basically. And yeah, these are I believe these are oil returns, and under these are the head bolt studs, also in these same shapes here. So, and yeah, you can see the cooling system pockets here also. So you see some designs use these plates on the side, but it's very, very easy. I mean, of course, you can make plates work also. I mean, it's, yeah, not something that is bad per se. But if you see designs with these plates, then you really need to ask questions like, are these guys, like, do they actually know what they're doing with the cooling system, or do they just want to have some kind of a pocket to run cooling so that you can have the engine at idle or something like that? But will it provide enough cooling to be able to run circuit racing at full power continuously, for instance? That's completely yeah, another question. But yeah, so the end result is, and yeah, you can see these bumps here also. So these are for the connecting rod clearance. So the counterweights always have or well, in almost all cases typically have less clearance required than the connecting rod. So yeah, here you can see it clearly also. The counterweight clearance sections is here, and the connecting rod needs significantly more clearance, and yeah, the counterweight on the other side here. So these are, yeah, as tight as possible. And yeah, here you can see, for instance, one of the design aspects also for the dry sump system. So there is no oil pan at all. This cover here, this is here just solely to be able to, yeah, inspect the main bearings basically. And well, I mean, yeah, you can see a little bit about the main bearings. I mean, mostly it's the connecting rod bearings, because you can pull the connecting rod halves off with just removing this cover, so you don't need to disassemble anything on the oil system at all. And these are the oil extraction locations. So you can see we have a suction hole here, and this, of course, the size of this needs to be dimensioned correctly in relation to the dry sump pump you're running. And yeah, you can see some mounting through holes here, and this is an oil return hole from the cylinder head also, and this also needs to be dimensioned correctly, because it's super important to maintain a positive oil flow location, or oil flow direction from these holes into the pump, so that you don't have this like backwards and forwards moving flow that will like spew out some oil back into the crankcase, because you want to remove as much oil from there as possible, because that just creates oil foaming and yeah, friction losses, of course, and ends up coating the cylinder walls with more oil than you want. You want a really, really thin oil film there on the cylinders. And yeah, while I'm here with the close-up cam, let's take a look at our crankshaft here. So this is, yeah, one of the other aspects that we really, really heavily designed. So specifically this connecting area here between the main, you can see this is the main bearing surface, and this is the connecting rod big end bearing surface. And this shape here in between here is very, very complex, as you can see. And this, I mean, took quite a while to actually figure out how to even design this in CAD so that it's easy to change these parameters on this shape, and yeah, run multiple iterations of FEM calculations on this to figure out the different aspects on this. But yeah, this is also one of the things we wanted to do ourselves on the engine. And it's also yeah, let's just jump back to the main camera. So this was also, yeah, one of the really sort of main components that we really pushed the design forward on as much as possible. I mean, there are lots of crankshaft manufacturing companies that are good at manufacturing crankshafts, and you can order a crankshaft with the dimensions you want, and they will yeah, spit that out for you very reasonably quickly and yeah, efficiently with a workable design. But yeah, with those types of crankshafts, you get something that will be much heavier or compromised in other aspects. So there are multiple design considerations when you're designing a crankshaft. First of all, you have to look at, of course, the mass always with racing engines. So you want to have as lightweight of a crank as possible. But you also need to have the correct counterweight for each piston and rod assembly. And how much counterweight you want on that is kind of a little bit dependent on how much external vibrations you can tolerate on the engine. Because inline 4 engine, for instance, is really good. The primary imbalance is, or the primary imbalance due to each cylinder is basically balanced out evenly inside the engine. So you could theoretically run with 0 counterweights, but then you end up increasing the load on the main bearings. So yeah, and without like super accurate values for what kind of bearing loading you can run on that, yeah, you definitely need to run counterweights, and those counterweights also help with crankshaft flex a little bit. So that is something to be taken into consideration also. And of course, though, the crankshaft flex is also, yeah, one of the design considerations. So you want to have it as lightweight as possible, as stiff as possible. You also want to have the natural frequency. Basically, it's always better to have a higher natural frequency, which is, yeah, basically the torsional stiffness, which is, again, there are, yeah, stiffness is in multiple different dimensions that you have to look into on the crankshaft. But yeah, that natural frequency. Wait, how many were we at now? So mass, counterweight amount, natural frequency, stiffness, and yeah, then you also need to look at what the durability of the crankshaft is going to be. So this is where this okay, yeah, you guys can see it on the camera. So that is where this shape comes in. So having as smooth transitions as possible, because if you have a high load area that is has a significantly higher load that is in tension than areas beside it, the materials will start fatiguing there. So that is also something you need to take into consideration. If you have an even high load, that's much better for fatigue than having a very local high load. So yeah, it took multiple design iterations, but yeah, we finally figured out how to get this like super complex shape, like just perfect right. Like if there's 1 millimeter more material or 1 millimeter less material anywhere in that strange shape, then the overall crankshaft design is much worse. And you, of course, also when you're designing the crankshaft, you also have to take, of course, the manufacturability into account. So you basically have 6 constraints, I think I'm up to now or something. That's actually more than I anticipated. Yeah, but anyway, so, ooh, and also the oiling aspect. Yeah, so we're up to 7 now, I think. Wow, I thought there were initially only 4, but okay, yeah, definitely at least 7. So it's this many. Anyway, so the oiling aspect is something we also concentrated on heavily, because you see a lot of connecting rod like big end bearing failures at higher RPM, especially if you're not running vibration damper or something like that on the engine, so you have high vibrations, and then you need to run very, very high oil pressures on some crankshaft designs to get that to work. But this is something that I wanted to reduce as much as possible. So we have these are cross drilled from the main bearings to each connecting rod bearing, and this helps you, well, not hugely, or depending on what kind of RPM you're running. The higher the RPM you run on the engine, the more of influence that is. It's more difficult to manufacture also, and yeah, it created some huge headaches for us also that we just barely managed to save once. But yeah, so it is much more difficult to manufacture that cross drilling, but it also means that from the main bearing surfaces, so typically they're manufactured with cross drilling or like through drilling the main bearing surface. But if you do that, you end up having to push oil from, so if you have a round surface like this, you end up having, well, I can't show really from that, yeah. So if you have a round surface here that is rotating very quickly, you have a centrifugal force trying to push everything out. So when you're trying to push oil in from the outer radius, you need a lot of pressure to overcome that centrifugal force to get the oil into the center of the crankshaft, where it typically then is drilled out to the connecting rod big end bearing surface. But doing a cross drilling with that and optimizing those angles heavily, we can reduce that so that you barely need any kind of pressure at all to just be able to get the oil in just a little bit inside the surface of the main bearing, and then it immediately starts radiating outwards to the connecting rod bearing. So then the engine is capable of running at a much lower oil pressure, and that is of course something that is important to have that capability. So you can either use that to either improve durability, increase the sort of flexibility on what kind of oil pump you have, or you don't necessarily need to have the oil pump chosen very, very accurately if you have a sort of wider margin of pressures that you're capable of running. And of course, for the piston cooling, of course, the oil pressure is another question again, because we're running dual oil squirters on this engine. That's basically to get oil to the bottom side of the piston to cool that, because most of the cooling from the piston is actually through the piston rings to the cylinder wall. And that of course, the larger the bore, the worse the sort of surface area of the piston ratio to the ring surface area you have. So the larger the bore you're running at and the higher continuous power you're running, the more other cooling you need to supply to the piston. And yeah, that's basically why we're trying to squirt as much oil as possible on the bottom side of the piston, while at the same time keeping excess oil amount from the cylinder walls. And that is something that is very difficult to do. But also, I mean, the dry sump system helps a lot with that. So you can squirt a lot of oil onto the bottom of the piston, but angle those squirters as accurately as possible. Of course, in corners with high G-forces, there's nothing you can do about that. You're going to get oil on the cylinder wall anyway. But for running in the straight and stuff like that, I mean, it will help then, and that averages out over a while so that you don't have big problems all the time at least. And running a dry sump system, you can then get all that excess oil out so that it doesn't end up rotating around at the crankshaft, pushing that oil back up on the cylinder walls and creating these sort of thick walls that are not good for performance. So yeah, there are a huge amount of these different parameters and things to think about. And again, I feel that to do these things very efficiently, you have to be aware of all of these parameters and then just basically ballpark everything, because you don't have time to calculate everything. And okay, yeah, you can cool the pistons more efficiently when the piston is moving up if you have higher oil pressure, because then the velocity of the oil coming out of the oil squirters is higher, so you can cool the piston further, like on a larger portion of the upward stroke, and you can get much more cooling time out of each stroke on the piston. But again, I mean, these are things that with our time frame, there was no possibility of calculating that. We just need to know, okay, there are these aspects, and what kind of compromises are we doing in which stage, and how could we improve things as much as possible to reduce the risks of having like a major problem that would require a big redesign to make things to work. And So the cooling system is another one of those. So we have a cooling inlet here, and we have a coolant exit at the cylinder head at the rear here. I mean, that's not anything unconventional or anything like that, but it's something that we went backwards and forwards with Rada a little bit on that, because the PR Tech team of course wanted to keep the factory cooling as much as possible, so they would need to redo as little piping as possible, and there were less restrictions on where to place the fire, like how close the engine could get to the firewall, depending on where the pipes need to be routed, or would they interfere with the exhaust manifold on the other side of the engine, and these type of questions. So like, okay, like I can't say for sure, but the cooling system is one of the biggest question marks, and I want to both help the head gasket situation as much as possible, and the cooling system as overall as much as possible by running this type of a system. So the 968 engine has the coolant exit at the front of the cylinder head and the coolant entry at the front of the block. So that basically means that the temperature delta you have in the coolant in the engine block while it heats up is at a maximum amount here at the cylinder 1. So that basically means you have a lot of expansion on the cylinder head because it's warmer than the block. So you have a big thermal expansion difference here on cylinder 1, which can potentially cause problems with head gasket sealing, for instance. And then again, if you run that system, then cylinder 4 will have a very even temperature. So you have this big compromise. But yeah, with this sort of a through flow system, and I mean, this isn't anything special. There are lots of OEM, or ordinary street cars that run this type of a cooling system. So you have entry in the block at one end, and exit on the cylinder head on the other end. So then you have the coolant flow sort of going through the whole engine at angle. That basically means that yes, you have higher temperature on cylinder 4 than you have at cylinder 1, but the temperature difference between the block and the cylinder at cylinder 1 is very low, because you have the same coolant basically running through that, and the temperature difference between the block and the head is very, very even throughout the whole engine. And that means that the head to block surfaces move much less in relation to each other, and that improves the sealing capability of the head gaskets a lot. So that is something that we wanted to do, and that, I mean, was super good to go through with Rod. Also, it was like going over the things with, I'm assuming, Richard over at PR Tech, and okay, Elmer Racing is saying that they have these things, and it makes sense, and he wants to sort of reduce the risk of having problems with the cooling system in the engine. And okay, so then they end up, okay, fine, we'll redo the piping, and that is less work than the potential risk of having to redo the design or having a problem with the cooling system. So the cooling system design in the cylinder head, that is of course, but that is something we want to keep secret. But I mean, there are no really big secrets there, though. It's just a question of design time, really, and knowing how to prioritize things and being really creative with your machining capabilities. Of course, with cast cylinder heads, that's not as much of a problem, because you can do shapes and stuff that are not reachable by machining. So you definitely need different designs with the billet head than what you can do on a cast head that the OEM stuffs do. But doing a billet component, of course, you can develop that much quicker than a cast head. I think the quickest quotes I've heard for like any kind of aftermarket companies, even doing cast heads, are like a 1 month plus or something like that, just for the manufacturing, and that's really slow. And you're still limited. You need to use castable. If you're using aluminum alloy, you need to use alloy that is castable, and that limits how strong material you can use. And even though you have if you use a really high quality and sort of really good place to cast your head, there's still always the possibility, or there kind of always is a possibility of material failure, of course. But with casting process, that is much higher than with the billet product, because you have a much higher likelihood of there being some kind of initial crack that almost can go through that. And I think there was a really unexpected complete engine failure in Australia, the supercar V8 engines, I believe. Was it earlier this year or or last year or something like that, that had just a piece from the casting basically fall off inside the cylinder head, and that ended up locking up one of the camshafts, and yeah, that tore the camshaft drive system, of course, off, and that threw the other camshaft also off, and all of the valves hit the pistons on that side of the V8 engine, and yeah, complete. Well, I mean, not everything was destroyed, but I mean, a complete failure basically of the engine. So I mean, things can happen. Of course, that can happen with the billet engine also, but it's orders of magnitude lower likelihood of that, because the billet material is so much easier to produce that there is a much lower likelihood of there being critical cracks in that raw material that you're working with. So of course, yeah, clear benefits, but clear challenges also. So design-wise, really, you have so many different components or parts of the design that all want to be in the same place. So you need to have cylinder head bolts, and you need to have the clamping forces that goes through those, figure that out, how to get those to work together with the block to get the clamping forces correct and distributed correctly also, which is apparently something no one does, which I don't know why, because that is something that you absolutely have to do. Yeah, what else? Then you have to have the intake and exhaust ports, of course, and you need to optimize both the shape and the sort of cross-sectional area over distance to valves, so that you have the correct design for that, so you can optimize the pulse tuning effects, because that has a huge influence on the engine performance and the RPM range you can use. What else? Yeah, you need to have the valve train, so you need to get the have the valves in there. You need to have the coolant also. You have to have the oil feed and oil return, or unless you're running an external oil return also, that makes things easier. But in this case, we're running an internal oil return, so we have as few external fittings as possible, because the more fittings you have, the higher likelihood you have of one of those fittings leaking. And yeah, it really ends up being like this huge, basically Tetris game, where you're trying to make everything work as well as possible, and some of the components have higher priority than the other ones, but for some components it's enough that it just like works well enough, but doesn't need to be hugely optimized. So the cooling system, for instance, it just needs to work well enough, but on the ports, for instance, you can always optimize those further, and if you can move things a little bit more out of the way so you can get a little bit better shape in there, then that's beneficial. But on the cooling system, for instance, or the oil feed, if that works well enough, then you're basically good to go. And of course, yeah, you need to, with the valve train and the oil feed system, you need to ensure that you don't have like oil buildup in areas, for instance, around the valves or something like that you would end up submerging things in oil or something. So you need to have oil draining possibilities, and also taking cornering into consideration. So if you're running like RP968 at 3+ Gs maximum in high-speed corners, then yeah, the sort of the oil level isn't flat or in 45 degrees. That would be at a 1 G side load. So the oil is really high up on the side and the corners there, and you need to ensure that in all of these like oil level different angles that the oiling system is still working, because in some of the fast corners in racetracks, I mean, you could end up running for multiple seconds at really high loads. So you need to, I mean, the oil feed amount, of course, also is one question. If your oil feed requirement is low enough, then you can basically survive through a corner even though your oil is building up in some area, and then just drain that out on the straights again or something like that. So something that isn't as difficult, but still needs to be taken into consideration. And design-wise, so the cylinder head is really difficult to get all the pieces to fit and work together and still be machinable. On the engine block casing and the lower half, for instance, being able to machine those is not difficult. I mean, if you have a well set up 5-axis machine and you have a machinist that can actually know what he does, that probably, I mean, Axel that does machining over at us is probably one of the top 5-axis machining guys in the world, I would guess. So definitely capable of doing that. And there are no super difficult to machine things, but it's just a question of how much time it takes to get things done, and you can't like stretch that time out forever, because you need to get parts done in some kind of a timely manner to be able to have a reasonable cost and a reasonable price for that component. And but yeah, so pushing this design, basically you can't just like start with a square block and then like sculpture in some things on the side. You're never going to be able to get to this level of a design if you do that. So getting all of these shapes to conform to the things that are on the inside and have correct wall thicknesses around the different areas, you basically need a much more complex setup to do that, which we've actually developed further and can do this more efficiently and slightly easier also than what we did on this Thor block. But yeah, we did do some innovations on this, but that is, yeah, probably would be a whole video just on doing that. But I mean, yeah, let me know if you guys want us to do eventually at some time a series on CAD design and how to make these types of shapes. Then yeah, leave comments and we can see if we can make that happen. But yeah, back to this Thor. So once we had the design of these components, and yeah, we did the crankshaft and stuff, we started looking, okay, like, are we at a sort of good enough level, and what kind of what does this whole package look like? And we were like, okay, estimating some of the components, of course, because we didn't have the dry sump pump, for instance. We didn't have a weight for that, or some of these other components. But yeah, we got a long block weight of around 106 kilograms, and we're like, okay, this is not too bad. Like yeah, it's designed for 1,500 horsepower circuit racing use. A long block weight of 106 kilograms. That's like way lower than anything you can buy from anywhere else, and especially considering this is an engine that is very easy to tune also for circuit racing. So you don't have these huge boost levels, and you need anti-lag stuff or something like that, or you have a super narrow power band or something like this. Like, this is a very easy to use and tune engine, but still provides a very high power to mass ratio. So yeah, that was really good and really sort of confirmed our design criteria, like what kind of an engine design do we want to start off with, what kind of dimensions, how much time and effort do we want to put into each of these different components and sections, and can we make that time frame work or not. And yeah, oh man, that time frame was very tight. So we did this whole design and manufacturing with a really small team, and yeah, but that is kind of not the whole story, because I think I estimated that I did somewhere between 80 and 100 hours, something like that, design on this engine during that. Well, I mean, not the full 9-month period, because yeah, we left for the or had all the components shipped over like a couple of weeks before the race, so a little bit shorter time than that. And we had some idle time in between there where we had some issues, which I'll get to shortly. But yeah, really long days, and yeah, weekends, of course, also absolutely flat out designing this, trying to keep all other work and distractions to as a minimum level as possible. And yeah, I had multiple times when just pulled a really long day, 12-hour day plus, and yeah, headed back home and sent over a update to Rod or something for the car, and said, okay, yeah, the other stuff we shipped last Thursday, hopefully you guys got those on Friday over there, or was it Wednesday, or I don't remember exactly which day it was that it needed to ship to arrive by Friday. But yeah, got back messages like, okay, yeah, they got those on Friday, like perfect. And yeah, multiple times, yeah, had gotten back home after a really long day. Rod sent over a message like, oh yeah, this guy that is doing the cylinder boring, or I don't remember actually the details on what it was. Oh, it was actually, yeah, some ducting pieces for the oil extraction system that they had to manufacture over there, because we were running out of time to get that done here in time, so the shipping would have eaten up the time. And yeah, I needed to send some files over. There was a problem with the file that I sent over, and I'm like, so yeah, we like understood each other perfectly, so don't need to go back and forth like, okay, what to do? I just asked him like, okay, like, is this like time critical? Do I have to go back to the shop now, or can it wait till tomorrow? And sometimes people are like, okay, yeah, I mean, this can wait till tomorrow, no problem. And other things are like, yeah, this needs to happen now. I'm like, okay, fine. Jump back in the car, head over back to the shop, do the modification, or like re-export the CAD file and repackage that and send that over again. And yeah, then on rather than sending over WhatsApp and email and checking, okay, yeah, no, you got the file, it works, okay, perfect. And then I go back home, try to get some sleep before the next day. So, but yeah, but that is also like, it sort of sounds maybe bad, but hopefully you guys could see like how enthusiastic I was about that. I mean, it was super fun work to be doing something as super high end as this, and yeah, trying to like figure out where to save time and where you can't save time, and okay, what things to optimize. Like, okay, can we save 2 kilos on this? Okay, if we can, then it's worth to invest a lot of time in doing that. And okay, can we like potentially save like 2 days of calculation if we just like ballpark these injectors, or so the oil injectors, for instance, for the underside of the piston. Like, can we just ballpark these and hope it works? Yeah, we can probably get away with that. Okay, let's save time on that and not look into that at all. Just specify whatever and go with that. And yeah, we'll see how it goes. And did we make it to the 2017 race or not? We did have some problems also, which put this into a lot of question, because we were looking reasonably good at the time frame there, sort of early summer, something like that. But that was in, what was that, 2017, yeah. So that was when there was a big exploit in the Windows SMB system, where there were, yeah, hospitals and things like this that were completely closed due to that system or that exploit being used to completely just like shut down lots of systems. And TNT that we're using at the time, and that they used over there also to ship components over to us to take dimensions from and stuff like that, they were heavily affected by that. So it wasn't just like government-run things, or I think there were probably private hospitals also. But yeah, TNT was heavily affected by that. So basically had a component that they shipped over to us that got stuck in EU customs, because the paperwork basically was there, but their system was fully crashed, so they couldn't access that. And they hadn't specifically informed us that they were shipping over the component, so we weren't expecting the component. We were just wondering, like yeah, we kind of need to get a move on. Like, we've been waiting here for like a couple of weeks now, and like we need to know how we're going to proceed with this. And I got a message back like, what, you haven't received the part already? Like, yeah, we need you to design this thing. And we're like, oh crap, what's happened? Like, we haven't got any kind of information at all. And then we figured out, okay, it's stuck in EU customs. And then it took, I'm not sure, I mean, we were fully panicked, like calling over to TNT and trying to bombard them, like, okay, we need this part like immediately. I mean, this whole project is being held up because of this. And yeah, I don't care. I mean, we have the documents. I mean, we can email those over or whatever you need. We need to get that going now, or kind of like fly over and get the part from wherever that EU customs location is, and I can like give the paperwork over to the customs guy and like take the package with me on like carry-on luggage back here to Finland or something like that. Like come on, we need to get things moving. And yeah, they were, of course, I mean, as helpful as possible. I mean, they of course had system failures, so I mean, things can happen with that. I mean, we try to minimize that risk here, and so far we haven't had problems with that, or significant problems with that, so that's good. And yeah, we have backup system and stuff like that have always saved us so far. But yeah, so I mean, it can happen to everyone, of course. So not like trying to trash talk TNT or anything like that. But I mean, yeah, the guys there helped us quite a lot, and we finally got the thing moving. And I believe, yeah, that TNT, I don't remember how that worked, but they somehow like got confirmation, like, okay, like if there are some fees or something like this, that we can pay them later or something like that, so they can get the package moving. They got that over here, and yeah, we continued with work, but we lost, I think we lost about a month of time on that. I mean, of course, we worked a little bit on other aspects of the design while we were waiting on that one component, but yeah, that really put us back also a lot. So time was very, very tight to get things over for a World Time Attack 2017. But yeah, I'm not going to go through that now, because this video is way too long, and the next episode 3, will be about World Time Attack 2017. So stay tuned for that, guys. And yeah, I'm Oscar from Elmer Racing, and this has been episode 2 of our what is this? This series even. Yeah, Thor the story. And yeah, this was Sweat and Sore Mouse Arms. See you in the next one. Bye.